Okay, what is happening? Here we go.
Yeah, we're on YouTube. That's good.
Awesome. Well, hello, everybody in VJug land. It's so nice of you to join us today here for our session. So without further ado, let's kick this baby off. And as they say, in every single call you have been on for the last year plus, let me share my screen. Okay, so again, thank you for joining the virtual Java user group. My name, if I can remember it, I can't, is Lori LaRusso, and I work for JFrog. I'm one of our community managers here. And if you have any questions, you can hit me up on Twitter at Lori LaRusso, and I'm also in the VJug Slack channel. We'd like to thank our sponsor, Sneak, who make this possible. They connect us to the YouTube Zoom service. They're amazing. And yeah, thanks, Brian. Thanks, Simon. If you have any questions, hit us up on the virtual Jug Slack channel with the hash in the live stream channel. You can share this session with anybody you want. And if you have any feedback, please hit us up at Virtual Jug on Twitter. So now that I am done with my hosting duties, let me please welcome to the stage Richard and Sadiq. They are going to present No Free Lunch, Memory Allocation in the JVM. And with that, let me hand it over.
Great. I'm just going to share my screen. So share. Right. Great. So, hello, welcome to this talk. I'm Sadiq, and here is
I'm Richard. Hello.
Great. We're from Optimisations, performance tooling and consultancy company. Now, I'd normally make some joke about this being we normally do this at conferences. We do talks at conferences, and I would normally make a joke about there being no free lunch at this conference because it's virtual because there's a pandemic. But this is VJug, so there's actually no lunches anyway, so the joke doesn't really work so well. But still, the talk is going to be about memory allocation in the JVM. So how it works, why it's not free, why it's hard to reason about, and then what tools you can use to better understand the allocation behavior of your programs.
Yeah, and I'm sure there are people out there who are thinking, look, I've got an IDE, I love my IDE, it works great, and I'll just read the code. Well, and that will help me solve and understand different performance problems. But actually, we're going to talk here about the #1 way in which software engineers can improve their performance optimization skills. It's really simple, it's something we can all do, and it's something that we see so few of our fellow engineers not doing, so few of our fellow engineers doing, and it really hinders their ability to better optimized systems. And that thing is to measure before jumping in to read the code. So it's good to read your code to understand it. But what we really want to do is take a more scientific approach, an approach grounded in measurement and testing, rather than just reading code and theorizing about what we think it does in the abstract. So this talk's going to cover a few different topics. Firstly, we're going to talk about what allocation actually is. You know, there's no malloc in Java, so why would we worry about allocation? Does Java really do allocation? Then we're going to have a look at how it works under the hood, why there's a cost associated with it, a performance cost that's not free in performance terms, how you reason about memory allocation, like why that's hard and how you can reason about it. So firstly, what do we mean by memory allocation? Well, we've got an example here on screen, a method called foo, and foo has got two variables in, A and B. Now, A involves no allocation. It's a primitive variable, it's an int, and its value is 42. And there's no allocation with variable A, because A is a primitive type and the primitive type can just live there on the stack frame and not be allocated. B, on the other hand, does need to be allocated, okay? And that's because B is an object. It's of type myObject. And that's an object that we need to put its value somewhere. And its value is going to live on the heap in the Java application. So allocation really is about finding a space inside your Java heap which you can put the value of an object, okay? Now, it's worth noting that not every type of allocation necessarily requires the new keyword in order for an allocation to happen. We're going to look at some examples later. So auto boxing in the JVM is one example of that. String concatenation is another example where that can happen, for example. And to make things a little bit more complicated, I've said that this code allocates an object, but actually there are certain optimisations that can remove object allocation from your JVM process, from your running Java application. So it's not 100% sure from reading the code whether there's an allocation there or not. And we're going to see more on that story later. So,
right. That's all right.
Yeah, so how does allocation work?
Okay, so Rich has covered what allocation, defined allocation, right? So Rich has defined allocation, and we've said it's the reservation of memory in the heap for an object, right? So, but how exactly does the JVM carry this out, right? So, sorry, there we go. How exactly does the JVM carry this out? For most allocations, the JVM uses a technique called pointer bumping. So this is where you have a fixed allocation region and we have a pointer to a position in it. And when we want to do an allocation, we increment the pointer by the size of the object that we want to reserve memory for, right? Now, size here is the size of the object's fields and the size of the header together, right? So what we do is we have this pointer and we increment it or bump it by the size of the object, right? And we keep on doing that, and we can do that for the entire allocation region, right? So it's a fairly cheap operation. We basically just add a number. Now, it's worth pointing out that this is the fast path for objects. Some objects that are deemed large by the GC, so they're above some threshold, they'll go by potentially via a different, slower path. But that's fine because you tend not to allocate very large objects very, very frequently. And if you do, you might have other problems. So we've said what we do in the normal case, that we bump this pointer along in the allocation region. But what do we do when we get to the end of this allocation region? Well, that's where the GC comes into play. At this point, you call it the garbage collector, and you'd say, look, over the end of my allocation region, can I have some more space? And the GC could have some more space for you, could have another region to allocate into, and it might hand that to us. But also it might have determined actually that there's no more space, and we need to kick up off a collection of some kind or to free up some space to give you to allocate into. Now, the actual mechanism by which that happens and the collection itself depends a lot on what the garbage collection algorithm you're using is. If it's the parallel collector or CMS or C1, this might be a stop the world minor collection where all the threads are stopped and some more space is reclaimed. But it could also kick off a full collection depending on how much of the heap has been used. And for the concurrent collectors like ZGC and Shenandoah, this might start a new kind of cycle of work that happens concurrently with the application to try and free up some more space. So we looked at the high level of what happens with pointer bumping. But on this side, what we're going to do is we actually look at the nitty gritty. So we're going to look at some simplified assembly. And now this assembly code is derived from assembly generated by Java 8 JVM, by the parallel collector. And what we've done, we've stripped out a few of the bits that aren't relevant, like prefetching or stats collection, but they don't really change things much. So the first thing that we do is we move the allocation pointer into a register. Now, depending on what architecture you're on, if you're on one with plentiful registers, then it might already be cached in a register. So we move the allocation, the allocation pointer into register. Then we add the object size, and then we compare that with the end of the allocation region. If we're over the end of the region, then we call into the GC. If not, then we update the allocation pointer to new location and begin populating the object. And this is really cheap. Like on the happy path, this is very, very cheap. The branch predictor will almost certainly always predict that we won't be over the end of the region because it happens so infrequently. And so this ends up being a very, very cheap allocation mechanism. Now, the problem is what we've discussed works fine if you have a single thread, right? If you've got a single thing and you've got single core and a single thread, and you just got one thing that's doing this bumping and then checking and bumping and checking. Problem is, though, is that on modern machines, you might have multiple cores, and you may have many, many more threads than you have cores. And that creates the problem where if they all shared one pointer and they all competed to try and bump these pointers, then they would end up doing lots of shared writes. Now, shared writes on modern multi-core systems are very expensive. They don't scale very well, and they're very expensive to do. And so what the JVM does to avoid this is it uses thread local allocation buffers. So each thread has its own allocation buffer. Now, they're all parts of the JVM heap. They're literally just address ranges within the minor heap, but they're exclusive to a single thread. And what that means is that at any given time, you might have many threads running in parallel, that each allocating independently into their own local allocation buffers, but not coordinating between each other until they reach the end of an allocation region, right? At which point they call it to the GC, and GC decides to do something else.
Cool. So Sadiq's talked about modern smart garbage collectors, pointer bumping techniques, concurrent collectors. Great engineering work that's gone into garbage collectors over the years. And some people take that and they look at it and it's like, well, allocation is really fast, it's really efficient. We can basically treat it as though it's free, right? We can just allocate as many objects as we want. We don't need to worry about penalties. We don't need to worry about cost models. We don't need to worry about anything. But the reality is somewhat different. And in order to understand why this is the case, let's take a look at the memory hierarchy on modern CPUs. The memory hierarchy involves there being a bunch of different layers of memory. You've got your main memory, and above main memory, there's a bunch of caches that sit on CPU, L1, L2, L3. And the numbers on the slide, by the way, relate to AMD Zen 2 CPU. So fairly modern x86 type CPU. And the idea with your memory hierarchy is it works a bit like a pyramid. So the smaller, higher up memory hierarchy layers are also faster. So as we go up, things get faster. As we go down, things get bigger. Ferrari versus an SUV. And we've got access times on the left. So that's the latency of getting data from a tier of the memory hierarchy into a register. And that can be as low as 2 nanoseconds for L1 cache, and it could be well over 100, even 200 or more nanoseconds from main memory. On the bandwidth side, again, the bandwidth increases the further up we go, so 200 gigabytes a second at L1 and down to 25 lower down. And making good use of these caches is really important, because if your CPU can't get data from memory, it will stall and it can be slow. And the way that happens is you get cache washing or cache pollution. Now, normally, if you hear this kind of expression, you might think of money laundering, the mafia, Tony Soprano, whatever. This kind of cache washing isn't really a crime as such. You're not going to go to jail for doing it, but it can still have negative effects on the performance of your software application. Now, caches are most effective with a high hit rate. So hit rate is the percentage of attempts to access the memory that actually are within that layer of the cache. The higher the hit rate, the faster things go, the more effective they are. But as you allocate lots and lots of objects within your JVM, that writes data into different layers of the cache. Now, if you're going to immediately read that data afterwards, that's kind of fair enough. And that is often the case, but you have to be aware that by allocating lots of objects and by cycling through memory, you tend to remove old data from the cache when you run out of space and by writing new data into it. Now, modern CPUs are write back rather than write through. So that means that instead of writing the data all the way through to main memory, they just write it to the cache and then send it back to main memory later on as it gets evicted. Now, that minimizes the impact of this kind of write level on the memory bandwidth between your CPU cache and your main memory, but ultimately, you're still reducing the effectiveness of those caches. This reduces the efficiency of your system and increases CPU stalls. So CPU stalls are times when your CPU wants to do work. It's sitting there, waiting, unemployed, looking for work to do. And it's got to get data from a cache or from the main memory to come into the CPU in order to do that work. This often isn't things that are very visible to people's systems. Like it can look, if you look at VM, stat, or HTOP or a monitoring tool, like your system's doing 100% CPU work because a process is allocated to that CPU and it's working, but it's stalled. It's not actually able to make progress effectively. The other thing to be aware of with cache pollution is that when you run a garbage collector, that does some tracing over the heap, and it can also modify parts of the heap, move objects around, and that also has an impact of polluting the CPU cache. Again, we're not trying to hammer the great efforts that have been done by people maintaining garbage collectors, that they're very well engineered pieces of software, very well made, but there is an impact from using them on the system. Another impact that you get from allocation rates is just the sheer cost of allocations. So doing a garbage collection pause in order to clean up those objects does take up CPU, and it may also stop the world as well. So many collectors have stop the world pauses for minor collections. So the parallel collector does, that's the default in Java 8 or below. G1 does, which is the default in Java 9 or above. These stop your entire system periodically to do some garbage collection work. They're annoying, causes impactful latency, harming jitter operations, lots of things there. Modern concurrent collectors don't have that same stop the world pause problem. Like when I say a concurrent collector, I mean things like Shenandoah, ZGC, things like that, which is fantastic. Again, great work. People are writing garbage collectors, but there's still an impact in terms of having to do CPU work in the background to trace that heap, to figure out which objects are live, and in order to actually perform garbage collection work, sometimes might have a CPU cost as well. And again, there's still work there. The other thing to be aware of with some of these stop the world pause problems is it gets worse in a modern microservices heavy deployment environment. When you get those pauses that might look not too bad when you look at an individual machine, they can have more impactful behavior when you look at a whole system, and when you are considering for example, a fan-out style microservices architecture where you've got one service that talks to a bunch of others. And if multiple of those other services pause and the communication isn't overlapped, you can end up with an even bigger pause in terms of the user response and the user-facing operation at the end of the day. So microservices can also make this impact larger. Then there's time to save point, or TTSP, to use its acronym. TTSP is a big performance overhead sometimes, especially big if you've got a very modern, efficient concurrent collector. That's because concurrent collectors tend to make the actual collection part more efficient. They do tend to not actually need to hit save points that are global stop the world pauses that frequently, but usually concurrent collectors are collectors that do have global stop the world pause and just not ones that scale with the size of their heap. Now, what is time to save point? Well, when you want to perform a VM operation, like a stop the world garbage collection type operation, you need to bring the application threads to a halt in order to do that GC operation. And that process of bringing things to a halt, that's called a save point. That's when the threads poll bits of memory and they look to see whether they continue running. Some threads can take longer to reach save point poll points than others. We don't want to go too much into the details of this, but that can delay TTSP, especially in CPU intensive, loop intensive systems. You can see what the impact of this is on your running JVM application if you use the command line option -XX : plus print save point statistics. And the this time is especially impactful as the allocation rate increases, because that tends to cause more and more minor collections and trigger more and more VM operations within your system. And so the time to save point is there even as the efficiency of the collector improves. And finally, there's just the straight off CPU cost in terms of garbage collection cycles, in terms of GCs do need to do work, especially if they hit a degenerate case and they back off to full GC cycles. Now, you can hear some people arguing like, well, it's not really allocation work, it's more like objects living longer, but there are effects that cause that, like premature promotion, where higher allocation rates cause objects to survive young GC cycles and live into older tenure generations, and then it's more expensive to collect those tenure generations. These are true in both stop the world GCs and concurrent GCs. Stop the world GCs are worse, definitely, in this case, but concurrent GCs do tend to have background threads that are doing work that are eating up CPU, reducing the efficiency of your system. So it's definitely something to think about.
Great. So Rich has gone over some of the reasons why memory allocation isn't free. And we're going to now look at some of the reasons why allocation can be really hard to reason about just through code inspection itself. And then we'll look at why we need to measure in order to understand what's really happening. Right. So what we're going to look at is we're going to cover places where we expect allocation to happen, but none does. And then places where we don't expect allocation to happen, but it happens anyway, right? So in places where we don't expect allocation to happen, there's no keyword, no new keyword. So no new keyword, and yet allocation happens. So we're going to go look at both those cases. And both of those can make it hard to reason about the allocation behavior of code just by looking at it. So the first thing is autoboxing. This is where primitives that end up needing to be treated, they need to be treated as an object. So primitives normally are on the stack, local variables, but sometimes you need to treat them like an object, and that can happen for things like generic collections, right? So autoboxing was created as a usability thing to try and make using generic collections nicer. And what it would do is it will take a primitive and automatically heap allocate and put it into a box, and the auto-boxing thing. It's relatively easy to end up with unexpected allocation from auto-boxing. And so in this example here, what we're doing is we've got an array list of integers, so integer rather than ints. And then we've got a for loop, and what we're doing is we are looping over lots of ints, and we're adding them to this array list of integers, right? And this actually ends up allocating a whole bunch of integer objects, right? Now, to make matters a bit more confusing, it allocates, even though the loop is 1,000, it actually ends up allocating nearly 900 integers, not 1,000, because integers between -128 and 127, when ints with those values are auto-boxed, they actually turned into a cached integer, and that's because it's an optimization to avoid needing to allocate for frequently used short constants. Although this does lead to a rather hilarious situation where changing a numerical constant so it's slightly more suddenly means that you're now allocating a whole bunch of boxed integers throughout your code base where you weren't before. And And if you look at very high performance Java code bases that try to avoid allocations, ones that are very high performance doing low latency stuff, they nearly all use containers that are specialized to different data types, primarily to avoid this problem. So you'd see like int list and long list and those kind of things to avoid this auto boxing. The next example, the source of allocation that often catches people out, operations on strings. So in Java, strings are immutable, and so manipulating them often results in allocating new ones. And this is it's a rather simple but and not overly useful example where we concatenate the string representation of these different integers onto this string, and actually, interestingly, excessive string allocation was a problem early on in Java, and so the compiler itself tries to do a little bit of optimization to avoid it for simple things. So Java 8 and before, what it would do is it would turn the inside of this loop into a string builder, so it can potentially save you an allocation if X is short. Java 9, on the other hand, it translates the inner part of the loop into an invoke dynamic call, right, which takes X and the integer, so the string X and the integer I as parameters. And the intention here is that if you construct a call that has all of the data needing to be concatenated, you can make smarter decisions as to how to size allocations. So for example, if you've got, if you're concatenating 5 strings and these are all passed as parameters, you can determine the minimum exact length needed for the new string that you need to allocate by looking at the strings of all the parameters. So you can make smarter decisions about how you do these operations if you have them all passed as parameters. So that's what Java 9 does. So Java version aside, though, you could actually get away with putting a string builder outside here and then merely putting the appends inside, and that actually results in significantly fewer allocations due to the way that string builder's internal buffering works, in case you really wanted that code for some reason. Now, the next thing is immutable APIs and factory methods. A slightly more controversial. Now, immutable APIs are great, don't get me wrong. They can make things very easy to reason about. They can make knowing what operations are being done on data and whether it can be modified or not increases the your ability to reason about code and hence its reliability. But they do come with costs, right? So this is a factory method example. Actually, Richard, you can probably explain a bit about what happens behind this rather simple looking call here. You're actually muted at the moment, Richard. Okay, well, Richard's muted.
You probably expect a local date time, sorry about that, a local datetime.now method to allocate a local date object, but actually it does a load of things under the hood. Creates a system default zone, pulls the instant out of that, creates a system default zone clock, pulls the instant out of that clock, creates a zone offset out of that clock, and calculates the local date from the values there. So there's a lot of things going on under the hood. We're not using this example here to pick at this particular API. This is a really good API, but it's often the case that you're using libraries throughout your code base and you don't necessarily know what the allocation patterns are of those libraries under the hood. What might look like it's something simple can actually be quite complicated and can do lots of stuff under the hood and allocate lots of objects under the hood. And it's really difficult to understand what all the libraries and methods and APIs in your system are doing, especially the immutable ones.
Great. So what we've looked at so far is a few examples of places where where you haven't got an explicit new keyword and yet there's still allocation happening. Now, the reason why we highlight these is they're the kind of thing that you would see, say, in a code review on a pull request, right? Where you'd be looking to try and understand what the allocation behavior potentially of that code might be if it's on a performance critical path. And it's not always obvious looking at the code itself to understand what that allocation behavior is. So far we've looked at cases where there's no new keyword and yet you can have allocation. And now we're going to look at some cases where, or a case actually where you have the new keyword, but no allocation actually happens. So this is a rather simple vector. It's actually a vector 2D, got an X and Y, the doubles. and it's got this method squared distance, which returns the squared distance to another vector, right? And now we're going to use these vectors, and we're going to calculate the squared distance between two of them. So if you look at the code example on the left, you've got vector A, and it's some constants, vector B, and it's set some other constants, and now we're going to calculate D, the squared distance between A and B. Right. Now, we're going to go through two optimizations and one analysis that the JVM does that actually makes these vector allocations disappear, right? So the first optimization is inlining. So what is inlining? Inlining is where we take a method that's being called and we basically just copy it and paste it into the caller, right? So wherever it's being called, we just take its contents and in they go. And this is done for a couple of reasons. One is it can remove for when methods are small, it can remove the overhead of calling the method, right? You're not having to put arguments, store arguments and stuff, and then call and then jump and that kind of thing. But the second one that tends to be the bigger advantage is that actually it opens up more optimization opportunities, right? And we'll see how that happens in a second. Now, the next thing that happens is an escape analysis. So what escape analysis is it is a compiler analysis that essentially works out whether from the method it's allocated. What do we mean by escape? We mean that some reference to it can be seen outside of that method, right? It might persist, its lifetime might persist outside of the method in which it's allocated in. Right, and that can happen if it's assigned to the field of some other object, or some other object, or it is passed as a parameter to another method. Now, because we've inlined squared distance, the escape analysis can be sure that the two vectors we've allocated here don't escape at all, right? And so it can determine they don't escape, and then when it knows that, an optimization called scalar replacement kicks in. Now, what scalar replacement does is if you've got an object that doesn't escape and it meets certain other requirements, the fields actually essentially the object gets exploded into its fields, and the fields get turned into local variables, right? The object gets replaced by scalars. And where you've got primitives, this means that they are local variables and they end up on the stack, and that's actually what happens here. So these two vectors will turn into these local variables, local doubles, and no allocation actually happens, right? This is the code on the right is effectively what the JVM will produce once it's finished optimizing the code on the left. Now, that's great, right? It means that the JVM can cut out many allocations that would otherwise be unnecessary. The problem comes when you look at how this has happened. So what we did is we did this optimization first, where we inline this squared distance method. Now there's certain rules around what we can inline, right? We tend to only inline short methods. And so what happens if, for example, you make the squared distance method longer? You add some longer error handling or some logging or something along those lines, right? Now suddenly it doesn't meet the threshold for inlining, doesn't get inlined, and then the rest of the analyses and optimizations don't kick in, right? Now, another example, say, is if where the escape analysis fails, where again you might have logging, you might pass the 2D vector A and B into a log statement, and now it's seen to escape and is no longer replaced. And so now you have allocations where you didn't expect. So small changes to code that's not actually this code itself can actually cause it to allocate where it didn't before. Right. So that is an example of where we expect allocation to happen, but it doesn't. Right.
So we've talked about memory allocation rates being important, about the performance impact they can have, and also where they're really hard to reason about here. Like Steve talked about cases where it looked like allocation was happening, but it wasn't. It didn't look like allocation was happening, but it was. Lots of things to think about. Now, I can understand if you're watching, you might feel a bit down at this point. It's like, how are we going to cope with this stuff? What's the point? But don't worry, be happy. We can understand what's going on. We just need a little bit of measurement and some tooling in order to understand what's going on, a kind of an approach that's more tooling and measurement based rather than reading code based. So the first view that we're going to think about is memory allocation profiling. So allocation profiling is an approach for measuring what's going on within your system. If you run an allocation profile, you might see a kind of visualization like the slide on screen that's telling you some information about the memory allocation properties of your system. So memory allocation profiling is a way of saying, look, what are the types of objects within your system that are allocated the most? What corresponds to the big allocation hotspots? What are the worst offenders? And also things like capturing stack traces at the point of allocation. So that you can say, look, we were allocating a lot of char array objects, and those char array objects, where in our application or where in our libraries were we allocating those objects? What in my code base do I need to go and look at or change in order to improve and reduce the allocation profile? So that is the kind of output you're getting from a memory allocation profiler. And once you've been told, here are the big sources of allocation, you can look at your system and think, well, maybe I just need to focus a little bit on my char array operations. Maybe I need to focus a little bit on something else. Whatever the key bottleneck is, the dominant memory allocator is, those are the things you can look at and easily improve and iterate on. But it's also worth thinking about how memory profilers are implemented under the hood. So there are two different ways of doing that. One of them is using an instrumenting allocation profiler. So that's the kind of oldest, most traditional, most naive, maybe, way of implementing allocation profiling. Instrumenting allocation profilers do what they say on the tin. So they do what they say on the tin. So they find points in your application where you have allocation sites like new object, blah, 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 blah. Add a little bit of bytecode around that site. That's the instrumentation code that says, look, I'm going to capture some value about this object, like maybe what its type is and how much space it used up. And then store that value elsewhere. Now, the problem with instrumenting allocation profilers, when written naively, they have very, very, very high overhead. So if you allocate a lot, this code gets run a lot and it slows your application down. That slowing of your code down means you can't just run them in production. You can't run them always on. And we always like to have memory profiling tools that can be run always on in production, because that way you don't need to get your performance tests written. You don't need to do things like that. You can just look at what your real production system is doing and optimize that. The other problem with allocation profiling as implemented this way is it can defeat JVM optimizations. So inlining and escape analysis specifically, when you take an object and you take a reference to that object, and if your allocation profiler library is written in a way that takes a reference to your object and hands it to its agent code or its library code, then that means that a reference to that object has escaped. And if there were no other escaping references to that object within the method, well, that's a point at which you cause that object to allocate by defeating the escape analysis optimization and the escape analysis and the scalar replacement optimization that Sadiq talked about earlier. So that's a very challenging situation. A better way of implementing these things is using a sampling-based allocation profiler. So the idea behind sampling-based allocation profilers is we don't actually need to know the specific number of allocations of an object. What we really care about is, who ate all the pies? What are the biggest consumers of allocation? What are the dominant allocators? And that can be done by just triggering a measurement of the type and amount of memory allocated on events that are proportional to allocations. So you can do it when a TLAB gets refilled. You can do it when there's a minor collection going on in the JVM. And you can also configure the overhead there. So for example, you can do things like capturing stack trace only periodically when you get some events, and you can take fewer samples there.
Yeah,
Are you there, Steve?
yeah, Zoom has had a hiccup. Here you go.
Okay.
You should be back. Yeah, there you go.
Great. So you can configure the overhead there, you can reduce the overhead, and that means sampling allocation profilers can be made to be very, very low overhead. At Opsian, we have a sampling allocation profiler as part of our performance monitoring product, and that can have less than 1% overhead when run in production on people's systems, and people run it in production, and it has very, very little noticeable overhead and can be used in a production setting as a result of this low overhead. You have to be a little bit careful, even with sampling JVM, even with sampling allocation profiling, to make sure that other aspects of your agents don't cause problems with memory allocation. So for example, if you configure your JVM TI agent in order to inspect local variables and local variable information and get local variable debug information, then you can also do things like accidentally disable escape analysis based optimizations within the system. So there is other things like that that you need to be aware of or careful with when designing a sampling allocation profiler.
Great. So we are going to now go live, which is where things get a bit more interesting. And what we're going to do is we're going to look at a couple of examples here, right? Well, we're going to look at a bit of code. We're going to try and understand what that code might be doing. Zoom keeps signing me out. I don't actually understand what's happening here. All right, give me a second. No. Am I still in this call?
You are, yes, I can hear you.
You are, but your machine is not. Oh, there it is.
I don't understand. I didn't rejoin. It's just anyway.
Whoop, there it is. Oh, who's got that throwback to like the 90s, maybe 80s? I don't know. Am I showing my age?
All right. Okay. Good. Let's get through this before it kicks me out again. Right. So, okay. So we've got this. So we've got this bit of code here, and what we're going to do is we're going to look at this code as if we were looking at this and say a pull request, code review, and then we're going to go and I've actually run this, left this running against a server, and we're going to go look some allocation profiling data and try and understand what's actually happening and live. So, Richard, so we've got this example here. It's fairly basic. It's this remove duplicates method. You've got a list of integers. And what we do is we remove the first element from the list and then any duplicates from it, right? Simple stuff. What do you think the allocation behavior is going to be for this method?
I think you're trying to trick me here, Sadiq. As usual, I might add. You're going to get the first value out of that list, and you've not put that into an integer object, have you? You've put that into an int object first, and then you're going to compare that first object with the other boxed integer objects, and that's going to cause a boxing of that integer value when you call i.equals on the primitive int. So I reckon this is going to allocate a lot of integer objects due to that auto boxing that we talked about earlier.
All right, I think that's pretty reasonable. I'm sure people would agree. Now let's go have a look at what it actually does. So I am now going to switch over to, assuming I can. There we go. So this is a profile that I ran earlier. And so this is actually the profiling results from that bit of code. So what I did is I put a loop around it. I gave it this rather large list of integers, and I just left it running on one of our servers, right? And you can see here that the number one most allocated type is actually long arrays, not integers, right? So what is going on there, right? So let's look, and we can click on the type, and then we can see a stack trace of actually where it's being allocated from. So this example one, remove duplicates, great. So there's that's the method we're actually testing here. So let's go and have a look at what's going on. So I've got my IDE here. I am going to jump into the right place. There we go. Right. So here's our remove if. Can you see that all right? So here's the method that we have on the slide. It's this bit here. Now let's go and have a look at the implementation for remove if. Right. So we've got predicate, filter. I don't see any long arrays here, right? So what's going on? So if we go back and we look at the actual stack traces here, we see that we're not using collections.removeIf or collection remove if. We're using array list remove if. Now, why that's interesting is because if you look at the signature here, we are actually just passing a list, right? We're not, if you're just looking at that method in isolation, we're just passing a list. And so the best we can do is look at the implementation on that we have here. But because we have the runtime information, we can go and look at what the remove if implementation is on array list. Now that, it turns out that that's actually a far more complex implementation, because on array list, remove if actually supports it has some stronger guarantees than the remove if on collection. It supports the ability to access the array list itself inside the predicate. And in order to support that functionality, it has this rather morbidly named death row long array, right? And what that does is it stores the positions in the array list that need to be removed. And then right at the end, it goes through and removes all of those, right? Now, so that actually is what causes this allocation of long arrays, right? Now, it might seem like it's a, let me just try and, I've got somebody's asked in, can you see that? There you go. I've zoomed in a little bit, so you've got a bit more, you can see that it's a bit more zoomed in. Now, interestingly, this behavior actually changed between Java 8 and Java 14. So very quickly, we're just gonna have a look here. If we look at just the results for Java 8, I ran with both. We can see that in Java 8, the type that we allocated most of was integers. So somewhere along the way, yeah, well, Richard's smiling because
I was right all along. I was right all along. At least in Java 8, the best version.
But what we've seen here is that, like, it is that the actual behavior changes between Java versions, and if you were just looking at the code itself in isolation, then you wouldn't actually you wouldn't see that, right? And also it changes between these different Java versions. And this might seem like a contrived example, but actually this is very similar to something that we hit in a production code base that was actually the source of excess allocations on a critical path that wasn't obvious through code inspection, and that's on a code base that was high performance. So we're just going to jump back onto the slides, and we're now going to look at a slightly more complex example, but quite quickly because we're running out of time. We want to take some questions. So this is a larger system, and what I want to show here is that sometimes these problems can manifest themselves in weird ways. So this is in the UK, property transaction data. It's available online. You can go and download it in CSVs. And this is essentially a system that is a cache in front of an HTTP endpoint for this. So what we're going to do is I've been running this on one of our servers, and it's been monitored by Opsian Systems and JVM diagnostics tool. And there's a constant workload of requests that are hitting it. So now we're actually going to go and look and see how it actually what this dashboard is showing. Now, this dashboard has a lot of information on it. Let me zoom out actually here. It has a lot of information on it, and that is because it's designed to show you basically everything you need to be able to diagnose these weird and wonderful problems. But what we're going to do is we're going to look at a small subset of it so we can understand this problem. So let's start with application pause times. Application pause time is the ratio of time the application is actively running compared to the amount of time it spends paused, right? So you can see here this application is not behaving so well. At certain points in time, nearly 40% of, or more than 40% of its time is spent paused, right? That's generally a sign that's not too healthy, right? And if we scroll up, we can see that during those periods, it's doing a lot of CPU usage. And we can also then go and see that there are lots of these scavenge collections. This is running the Java 8 parallel collector. So it's doing a lot of scavenge collections at this point. And it's then also, we can go and have a look at the allocation rate. So what's happening here is actually during these periods, it's allocating quite heavily, right? Now, normally systems would stop at that point and say, well, okay, we're doing lots of allocations and go and inspect the code and try and figure out what's going on. But once you have profiling, what you can do is you can highlight a particular area and say, great, show me the allocation profiling information. And this gives you a breakdown of the allocation profiling information for just that segment in time. And if you click on the type, you can see where it's being allocated from. And generally, if you're seeing lots of chars and lots of chars followed by strings, generally a sign that you're doing excess string allocation somewhere. And it turns out in this case, the system is needlessly parsing CSV. We can go and have a look at where it's happening. So we can see this sales data here. Let's go and have a look at the code very quickly. And we can see that in sales data, this is actually an example system that we use for helping people do performance optimization stuff. And the bug actually here is that we've got this cache of data, but the cache is actually not being populated correctly. And if this system had lower traffic, you wouldn't see the excess GC behavior. You just see this system having moderately high CPU, but by having the diagnostics information and the profiling information, we can dive in a lot deeper and actually understand what's it actually doing, and is it behaving correctly. Right, so let's jump back. Back on the slides. Richard.
Cool, yeah. Thanks for demo, Steve, very interesting. The key takeaway from all this is, you want to avoid excess or unnecessary allocation. That doesn't mean prematurely optimizing things or adding custom object pooling implementations just because they look cool or sound cool, but often simplifying code, removing allocation can get you good performance wins. And the easiest way of finding out where that is using things like memory allocation profilers. Listen to Mary Kondo. Only reading the code does not spark joy. I'm pretty sure that's what she said. Similarly, the idea that you can just kind of read code and understand its memory allocation patterns when there's JIT compiler optimizations, libraries doing whatever they want under the hood, different cost models with different GCs, it's a thankless task. It's like pushing a rock up a hill. And memory profilers can help you overcome this problem. So it's a great tool to have in your tool belt, especially if it's a memory profile that can run in production, and then you can see what your real production system is doing. Memory profilers are like a measuring tape for object allocations. Easy to use, easy to find low-hanging fruit. There's often some really good optimization opportunities that are available if you look at where your memory allocation is coming from. And finally, that's the kind of conclusion to the talk. So we'll go through any questions that you've got on Slack just now. If you want a copy of the slides, you can just head on over to that tinyurl.com/allocation talk. And also you can send us any questions that you might have if you're watching this offline or later, because I know it's going on YouTube, via that URL, and we'll happily answer them. If you're interested in a free trial of any of our stuff, which includes a memory allocation profiler, you can head over to option.com. Some of our customers have described it like a magnifying glass for their servers. Okay, thank you very much.
Good. So I've just had Slack going here on the side, so Vivek, yeah, vector I will change this to vector 2D. Yes, I can see how vector might be. The vector that we have on here is not the vector from the java.util.vector. And so, yes, that it's not that one, if it was confusing, sorry. Hi, Manny. Thanks for linking the escape analysis blog post. That looks like a very interesting read. Do we have any other questions?
So Manny's also asked here, some talk about sample bias. Can you please talk about the pros and cons of using sampling allocation? So we did mention that earlier on the slide, where basically sampling-based allocation profilers don't give you the exact precise numbers in terms of allocations, but on the Pro, they're way, way less overhead, much more efficient, and you can use them in production.
Yeah, so Manny's got a question is, how is Opsien ensuring that you have the best of both worlds, get the most out of production information, and also not dampen performance or add to the observer effect? So sampling is, as Richard mentioned, sampling is something we rely on very heavily. We set ourselves a performance envelope when we implement features, and we have basically a test suite that we use to try and keep inside of that. So it is a bit of a game where you want to trade off to get as much information as you can, but while staying just inside of that envelope that you set.
It's also worth noting as well, on the specific issue of memory allocation, we have a native code agent that doesn't do any object allocation on the Java heap, whereas some monitoring tools do things like allocate objects on the Java heap as part of the processing of their agent, and that does have an impact and an overhead in terms of your system.
So Jose has a question. Why is Opsien solutions better than the free tools like memory analyzer from Eclipse using just sampling? Well, the way Opsien works is you run it all the time and you leave it on in production. So it's designed to be left on, and our customers install it and then they leave it running the entire time. And it is there collecting information, and it is sending that back to the Opsien appliance or our hosted service. And so you've got the data there whenever you want it. So if you come in tomorrow morning and people say, well, 2 o'clock last night, the system was performing slowly, we had some long GC pauses, what was the problem? You can go back in and say, show us just this profiling information at 2 o'clock in the morning, right? And you can look at the allocation profiling information, for example, or you can look at the GC collection information at just that period of time.
Sorry, I was going to say, just to add to what you were saying, because we've been talking quite a bit about product here, but I think there's also, even aside from our product, there's a general difference between the different types of tools there. The Eclipse Memory Analyzer Toolkit is a heap dump analyzer. So that means you take a dump of your entire heap and look at it on your system. That can be really difficult to do in practice as an approach with heaps that are really big. Like if your production system has 128 gig Java heap, which is not unreasonable given people use big servers, and you want to try and use the memory analyzer toolkit with huge heaps like that on a regular desktop or laptop, that can be really challenging to do. And also dumping that heap can cause a big overhead. So things like, even ignoring our product or whatever, the approach of having sampling, profiling information is something as an approach that can be run always on in production, whereas things like heap dump tools are quite difficult to always be gathering that information in general, regardless of how efficient it is made.
Yeah, and the other thing is, so many of the people who run Opsien do it because the engineers themselves who need that data don't actually have access to production systems. And so by making sure that the data goes directly from the production systems to an appliance where it's indexed and stuff, and access to it is via a web interface, they don't have the problems of, for example, shipping a heap dump around, which might have PII, person identifiable information or credit card information, whatever in it, which could be a security problem. So yeah. Manny's got a couple of questions. How do we handle outliers or multimodal allocation data? It's a good question. So what we try and do, and what we've been trying to do with the systems and JVM diagnostics work, is allow you to start exploring time, so that you can look and say, okay, well, during this time period, I've got an allocation report, and I can go forwards 5 or 10 minutes. And I can look at that point in time, and I can try and understand how it's changed between those 2 points in time, because otherwise it's quite hard to give that information. Next question was, do you have an alert system in case you have additional hooks?
Expand on what you're saying there as well, Steve, because it's not just about time, is it? Like, we also have things like, you can see the sequence of actual GC related events.
Yes.
And you can see things like full GCs and tenured GCs. So you can see those few but long outliers within that event-based data, that if you just took an average over a time period or over all GCs within that time window, that kind of information would be invisible. But by looking at things on an event basis, you can kind of see that information.
So Manny's next question was, do you have an alert system in case you want to add hooks and monitor allocations and other behavior? What we do for the first question, the JVM and systems diagnostic product comes out of the box with a bunch of alerts for common problems. So you can set a duration for the max pause time, time spent in pauses, and we also look for certain other behaviors that are good signs that something bad is happening to your application. There is support for custom alerts where we can add integrations with other custom. If we're doing a big deployment, we can add integrations with customers' alerting systems or add custom alerts, that kind of thing. Functionality is there for us to be able to do that kind of thing. Do you have also a way to monitor and report the footprint performance of Opsyn itself? We don't, but what we do advise customers to do is to A/B test it. And so far, we haven't yet found a customer whose own metrics are granular enough that they can actually see the impact that Opsyn has. But we are quite happy for people just to test it. So run it on some of their systems and test between the two before you roll it out to everything else.
Cool. So we have one question on YouTube, and I don't think you guys answered this one. It says, how to avoid allocation when using array list integer.add, where I is from a loop.
I think the answer for those kind of things is, if you've got primitive values, you're best off using a primitive specialized collection object. So when the grand future of Project Valhalla eventually comes to reality and Java has better generics implementation, then this is a problem that will go away. But for now, using primitive specialized collections is a good option. And you can get a high performance one of those in kind of open source libraries like Agrona or the Eclipse collections framework as well. And there's a few other collections frameworks out there that have primitive specialized collections, but that's the best choice if you want to have a collection of primitive objects.
Okay, everyone, we are hitting the top of the hour. So I'm going to do an all call for last question. Hit us up on the Slack, or I'm watching YouTube right now. And I'll do what I do with my daughter. I'll give you the 5 seconds. So we count down 5, 4, 3, 2, 1. Okay, y'all are behaving. And I just want to thank again Sadiq and Richard for today's session.
Right.
You guys were amazing. We had a lot of viewers on and lots of great comments already. So again, thank you everybody for joining VJug. Check out our meetup page. We try to bring you guys the best that Java has to offer from the best minds in the business. You can always hit me up on Twitter at Lori LaRusso at VirtualJug. And we are happy to take recommendations and suggestions on some new sessions and new speakers. So again, thank you guys. Have a wonderful rest of your day, whatever part of the world you're in. We're virtual all day, every day, and we appreciate you. So have a good day, guys. Thank you so much.
Thank you very much, Chair.
Thank you very much.
Thank you.